All right, Klaus, you're on. Introduce yourself.
Okay. First, I will share my screen. Okay, here we go. So since 2001, I have been developing my own force processor using VHDL for FPGAs. And it is not only a piece of hardware, it is a complete design environment. And today I'm going to speak about the software side of it. microForth, microCore assembler, because there is nothing below microForth, and interactive development environment. So in order to make it clear where we are, this is the design flow, and we are today, I'm talking about the green and circle 2 modules, which are the cross compiler and the debugger, which both run on a host PC. Characteristics. It's a command line oriented integrated development environment for microCore consisting of the microForth cross compiler. Then I'm talking about how to compile forward branches because it's special in microCore. It has libraries, it has a Umbilical Debugger, it has a cooperative Multitasker and Semaphors, it has a good mix or a full set of math instructions, and also it has floating point support. And if you want to get the full width of the word sets involved, please refer to microForth.pdf, which is on GitHub. The microForth cross compiler. So as I said, microCore assembler is a Forth dialect called microForth. I believe it is pretty close to the current standard, but I'm not a standard specialist, so this is just hope. But there is a special ramification because the cross compiler runs on a host PC, and only runtime code will be produced on the target. But the dictionary and the code that is only needed during compilation will remain on the host, which has two advantages. For one thing, no resource for the compiler, no resources of the target microCore systems are needed. And secondly, the development environment, the edit, compile, load, go cycle is much faster as if I would have to ship the source code over a umbilical link. The cross compiler has peephole optimization. For instance, tail calls are replaced by branches. When a load file is included, for instance, loadcore.fs, microForth is always loaded from source before compiling the application code, which means you are always using, in actual work, always using the latest version of microForth as laid down in the source code. microForth itself loads on top of GForce 0.262, and it is available as a Docker image. This is unfortunately necessary because I did have to patch and modify the existing GForce system in order to make the cross compiler elegant. but that locks me into this very version of GForce, and hopefully once GForce 1.0 is being distributed, it is currently being developed, I will probably port it to this latest GForce version. For instance, so cross-compiling. As we know in Forth, we have load screens, and just as an example, here is the load screen for load_core.fs. It is called core because it runs the core test program, which tests every single instruction on microCore. And so it's easy to check whether the correctness survived the latest changes. So when I start, I always start with the GForce image, and since I prefer to work in hex world, I also say hex. First, I include extensions .fs, which are a couple of Forth words I'm used to, but which are not present in GForce itself. Then I load the architecture description of the VHDL code. So the cross compiler and the actual hardware are always in step. And then the microCore cross compiler is loaded. So at that point here, the cross compiler is fully operational, and now I can start producing target code. So I say target to go into the target context, which means both the context points to the target dictionary and new words are compiled into the target dictionary. I say new to and that means a new target compilation is being made, and several variables are initialized. And then there is this strange word initialized. I have two operators, initialized and uninitialized, in order to control which interactive variable assignments and creates with commas after them will be automatically included in the boot code and will eventually initialize the data memory to the state which I defined interactively while preparing the source code. So here I say I want all variables and creates and such that they be marked as to be initialized. And the actual initialization is done in the boot routine by calling initialization. This is a trick to handle a forward reference in microForth, because the actual code for initialization is being produced automatically by the word add. And so at this point, it doesn't even exist. Then I include the constants, which are, amongst others, all the definitions that carry over from the VHDL code. I load the debugger. I load the Forth library, and here you see I do not include it. I say library Forth lib. I come to that later. And then I include core test.fs. Another thing, this little board that I'm using to do this has 8 LEDs on it. A quick show of my hardware. So this is the little board, and here are the LEDs, and you don't see them because they are not lit up.
We just see the screen.
Sorry, I have to go out of the screen share. Okay. And now you, why am I not on the screen right now? Kevin, can you put me on the screen as a main image?
I see a printed circuit board right now.
Ah, you see it. I see Samuel A. Falvo. amazingly.
Okay.
So this is a little board.
Brad, can you pin him or?
He's pinned on my screen, but I think others don't see that. Let me see if there's some other option. One second.
So this is a little board, and it has a number of interfaces. This is the RS-232 serial link for the umbilical. This is a programming adapter to configure the FPGA, and this is a power supply of the board. Okay. Ooh, and now I'm back. Okay, share screen. Okay, here we are back. Just as an example, here's a terminal and I'm connected to the board, hopefully. Yes, I am. So I now say include node core.fs. And it tells me that 3,234 instructions have been compiled. And now I can say boot image that ships the compiled code into the FPGA's program memory. And then I can say handshake, and that synchronizes both target and host. So that runs through without hiccup. And then I can go into the target by saying debug short for debug. And now you see I get the microCore prompt. I can execute core test and it returns a 0, which means everything is fine and we don't have any problems. Okay, so that was, oh, my cursor is gone. That is interesting. If I'm in the host, the cursor doesn't work anymore. Anything. So that was an example.
I could see your cursor even when you were in the host, so it may just be your local problem.
Yeah, I saw it as well, but I didn't move. It didn't move anymore. So this was an example load screen. And at the end of the load screen, here we see init LEDs. Init colon is a word that defines initialization procedures which get integrated in this initialization code. So I would say this is elegant and saves a lot of work. So then I define boot, and here are at the end are all the trap vectors of microCore which I initialize. So the reset goes to boot. The ISR interrupt service routine is the interrupt which has been defined in core test. The pause service routine just executes pause. In this very case, I have not loaded the multitasker. This is just a no-op. Then if I hit a break instruction, I come to this later. The debugger is called. And then I have a primitive for do-does. The starter store is so this is a single instruction for doing the initialization, and this is the, let's call it a soft call instruction, because with one 8-bit instruction, I can execute this sequence. So a very special thing is compiling forward branches. This is tricky because the branch offset may require multiple lit instruction preceding the branch instruction itself. Please remember, branches and such do not have their address information appended, but the address information precedes the actual the actual instruction that needs it. So when an if or while is compiled, an offset that fits into a single lit instruction is assumed. Not only the offset's address that has to be filled is pushed on the stack as usual, but also its source code location. Why? Because when the closing else then or repeat is encountered, its offset can be computed, and then we have two cases. Either the offset is less than 64, in which case it fits into a single lit, and we left the room for a single lit, and we are done. Otherwise, we now know how many lit instructions we will be needed, and the source code will be recompiled with a proper number of lit instructions in front of the branch. So this took me quite a while to get this correctly going, and it now works without hiccup, and it nests, and it can be used recursively. That means ifs inside of ifs and so on. And since everything is kept on the stack, it works. Libraries. This is a fairly recent addition to the system. Library forth libfs will pre-compile forth lib as a library. Pre-compilation means for each word in the library, a dictionary entry is created, but it is only compiling pointers to the word's source code, and it will not produce any code for the target in this step. And when a pre-compiled word is used later on during compilation or interactive interpretation via the umbilical, the word's source code will be loaded, producing actual target code. And this way, no dead code will be compiled at all. And so far, 3 libraries do exist: forth, task, and float. Alternatively, this is the nice thing about the libraries. Libraries can be loaded using include forth lib as usual, and that will immediately compile all the target code as usual. So this helps down to create compact object code images. The umbilical debugger. Host and target communicate via a 2-wire umbilical link in order to load microCore's program memory. You have seen this already, and to control microCore interactively via a terminal program on the host. The terminal always stays on the host, and in the latter case, that means terminal program on the host, one has the look and feel of an interactive forth system on the target itself. This is a typo here. So this is one part. Then we have a disassembler that allows to inspect the compiled code using show word name. And a single, we can do that. Like for instance, here we can say show core test, and we see that, well, the actual work is done here in parent core test, because this has to be caught when errors occur. So we should now say show parent core test. And we see what it does, and that's a lot. And here come all the test registers, test stack, call, and so on, and so on, and so on. So this gives you an impression of what is actually happening here. And then we also have a single-step tracer that allows to observe the stack while executing a colon definition using trace word name. And after every step, the stack can be manipulated, or one of the following commands can be used: nest, to follow a call instruction, and unnest to fall back into the calling word. And after, to continue single stepping behind a backward branch after finishing, and that result in that the remaining loop iterations will run at full speed, and the single stepper will only stop again when the loop has been finished. And another one is jump to skip the next instruction for debugging purposes if I observe that I did stupid things in the compiled code. And to give you an impression of how this works, I have prepared a small example. So I go into microCore, I include a file, include test.fs. This has loaded an example, and now I can say trace example. And so this will be the first instruction of the code in example, which is a literal instruction of 20. So it pushes a 20 on the stack. And the next instruction pushes an 8 on the stack. I can say, oh, I didn't want 8. I can say drop and put a 6 on the stack instead. So you see now I have a 6 there. And now I want to, and now I go into a loop via a call, and I can say nest. And then now you see there are 2 greater signs. Now I know, aha, I'm in nest level 2. It starts with a 2R and a branch, and now I'm at what has been created by the next instruction. I haven't showed you the source code. I will do this later. So we wind up at tor branch. The branches are not just finished because we have put 6 on the stack. So there is still at this point there was 6 on the stack, and now there is 5 on the stack. We do an R fetch. We get the address, and now we start. We store 5 at address 20. We say cell plus. Oh, this I didn't tell you. I started to convert microCore into a byte addressed machine if you want to. So there's a new parameter that tells you how many byte address bits are in an address, and if you have a 32-bit system, you have to set it to 2, because 2 bits for byte addressing, and then you have real byte addressing. If you don't want byte addressing at all, you just set the byte address width to 0, and then microCore works as always as before. So now we are at tor branch, and we remain in the loop, and set another store and cell plus, and now I say after in order to let the loop run, and then we encounter an exit, and that automatically brings us back into after this position in example, which is a no-op, and then we have an exit, and now I show you the mysterious code. Show example. No, we start with show a loop. No, this you saw. We need the source code, and unfortunately, I cannot show you the source code easily. But to solve the mystery, these instructions here are produced by query for, which will not run through the loop if the loop index is 0. And so the easiest way to do this is to immediately branch to the end of the loop, and then if it is a 0, it will immediately execute exit. If it is not 0, it will branch back to this point, which you have shown. Okay, so much about your umbilical debugger. The multitasker. The scheduler is a linked list of task control blocks. So one of this is a task control block. These are other task control blocks with a pointer to executable code that represents a task state. So priority has a pointer to the routine do prio. That's a do priority. At that point, I do a number of of performance computation, like for instance, which is very important, how many ticks did happen since the longest running task did a pause. So if there is a number greater than 1, then I will have to put another pause somewhere into the code. And then comes, and this anchor of the scheduler list is called priority because it is the anchor of the prioritized task. So here we have a prioritized task, which will, whenever a pause is executed by any task, I will go back to priority and then execute the first or probe the first task that is in the linked list. And eventually, if this task, for instance, is not active, so the code would be do go next, it points to the round robin link header, so to speak. And the round robin link header advances the link of the following circular list, which is the round robin list as we all know it, and advances it and changes it to the next task in the list. So the link pointer always alternates between pointing at terminal and pointing at T2. And so if we may have I don't remember the name when a task is active, but anyway. So this exit seg field actually is executed, and that handles is depending on the task state. Tasks and semaphores. microCore allows for 2 by the power of tasks address width tasks. So usually this is set to 3, so I have 8 tasks available using their own data and return stack areas. So task switches are fairly quick because the stack parts that reside in memory don't have to be copied. Task name creates a task. And a task is manipulated by pause, halt, wake, stop. So pause and halt are things that a task can apply to itself. Wake and stop are operations that another task can apply to some third task, or to some other task. And then we have activate and deactivate. I think that is pretty much in agreement what these words should do. Then we have schedule, which is new. Schedule tells us where a task has to be linked into this existing linked list. Then we have spawn. Spawn is a combination of schedule and activate. Cancel deschedules a list out of the linked list of tasks after closing any pending semaphores. And then we have an interesting word, which is poll and poll tmax. These are application specific. Well, let's take a look here. In this task, we would have do poll. And then we look at this, what we call user variable in the task control block, and we will execute this poll routine, which probes on flag, and depending on whether it is true or false, either wakes up the task or goes to the next task. And then poll Tmax is a combination of a polling routine to poll for a digital state and a maximum time that the polling is allowed. And I found that these task operators are all that is needed for task control. And we have semaphores. The semaphore name creates a semaphore. We can apply lock and unlock to it, and this is used for mutual exclusion. But we can also use the words wait and signal, and these are counting operators for synchronizing interrupts and tasks. So signal increments the semaphore by 1 every time it is executed, and wait waits until it is at least 1, and once it passes through, then it decrements the count by 1. And a full task switch consisting of putting the old task to sleep and waking up the new task takes 7 microseconds on a 25 megahertz system, which I believe is a very excellent value. Mass instructions. Several instructions allow for the following mathematical instructions when a hardware multiplier is present in the FPGA itself. Single and or dual cycle are times, m times, and times. And the times is a dual cycle instruction because it is followed by overflow detection instead of just throwing away the most significant word. And the overflow detection makes sure that it is either all ones for negative numbers or all zeros for positive numbers. And then we have bit step instructions for divide mod, for m divide mod. This is float division, for square root, and for logarithm dualis. And we have also floating point. Floating point numbers are data width wide, and therefore they can be handled on the data stack just like integers, which is very nice. Their exponent is exponent width wide, and therefore the mantissa is data width minus exponent width wide. In a 24-bit system, a 6-bit exponent and an 18-bit mantissa allows for meaningful floating point computation. I found this by experimentation and writing the code to convert an NTCs, so negative temperature coefficient resistor, from temperature to resistance and back from resistance to temperature. And this floating point computation that includes exponentiation and logarithm will still be stable with an 18-bit mantissa and a 6-bit exponent in the area, in the temperature area of interest. Then floating point I/O is usually responsible for about 16% of the code for a floating point package. And therefore, I have realized I/O as in a much simpler way, and I'm simply using integers, and we know how to print integers and how to include, for instance, integers into control loops by using scaling operators on the floating point level, which are called micro, milli, kilo, and mega. And I can even apply them several times if a result is way out of a normal magnitude. And that came to myself as a surprise. The floating point package only takes 500 instructions, including flog2 and fx2 transcendental functions. And in microCore, some instructions have been realized for floating point, and they are to float, to convert a dual number that consists of mantissa and exponent into a floating point, packed format, one could say, float from floating point number to mantissa and exponent, and normalize, that makes out of the dual number mantissa and exponent a normalized mantissa and exponent, and it needs one instruction per normalization step, but it is a self-terminating instruction because it recognizes when the normalization is finished. And then we also have the fractional times instruction as a hardware instruction available. So, and that was the end of today's presentation. And as usual, here are the links, and the floor is open for questions.
Can you tell us a little bit more about your single board computer?
About the single board computer?
Yeah.
Oh, yes,
if
it is.
Was desperately in love with it and felt that they absolutely had to have one, what would one do?
You would say yes and send me your mail me your email address, and I will send you one. I still have a number of them, and forget about the cost. That is going to be a gift. Well, yeah, the nice thing about it just contains the FPGA and the current regulators, the voltage regulators for 3.3 volt and 2.5 volt. For the 2.5 volt is if you use it for LVDS. And it has an RS-232 converter on it, and that's it. And besides that, it has lots of unused pins which can be routed to headers, and you can stick on other boards that do specific things.
Say again what the FPGA is?
That is a Lattice XP2-8E. So that is a fairly small one, but it is still big enough that a full version of 32-bit microCore with byte addressing takes a little bit more than half of the resources of the FPGA.
That's way cool. The way that the configuration of the FPGA gets into the FPGA is over a JTAG from your laptop?
Yes, I showed you the interface. So this is using one of the configuration dongles of Lattice.
So the schematics of the board and the artwork for the copper, are they available as well?
Oh yes, that's all available, or otherwise you couldn't do meaningful things with it on the unused outputs. You have to know where they are.
So we'd email you to ask for those. All right. Any other questions, comments?
If there are several people who want a board, I want to be paid 30 euros a piece. But then for me, the easiest way would be if one person in the US does a bulk order of the boards which are needed and then redistribute it from them from the US.
Klaus, to turn it on its head, could you use a standard Lattice board with the FPGA on it and then USB to TTL converter and two power supplies, no, two voltage regulators. I think that's how you described it.
Yeah, well, yeah, you can use standard lattice boards, but the standard experimentation board of the FPGA manufacturers tend to be packed with peripherals that you can play with. And so they cannot, yes, you can use them to explore microCore, of course, because you can just ignore all the peripherals. But you cannot do really meaningful things with it because they usually use up all the IOs of an FPGA.
Well, we did that with the 1802 that Steve Thiel did for me. And
Okay.
that just used the standard lattice FPGA board because
yeah, I don't know what a
interface is on
standard
there as well.
What is a standard FPGA board from Lattice? I don't know.
Well, if you go there, you always get at least one board where the chip is on, where you get a USB connection, and you get the headers.
Oh, okay. You get some such simple boards. Yeah.
Yeah. Standard.
Yeah, that's
Then
fine.
all the shipping problems disappear.
Yeah, all the shipping problems disappear. But then, of course, you have to adapt the pin out for the FPGA to the new board. And that's all at this instance that you actually have to adapt to.
Well, the pins are on the headers. It's just I/O, isn't it?
Now, yeah, but if you do a configuration of the FPGA, you have to tell the FPGA which signal goes on which pin.
Yes.
So that has to change, but everything else remains the same.
But in your design, as it is, they go somewhere. And as all the pins of the FPGA are accessible, they'll be in another position, but still there. But that would be an addition for you to do, basically an adaptation to a standard lattice board. So everybody in the world can try out a microCore.
That's a possibility. I take a note of it.
So what is the FPGA again?
XP2 LFX XP2-8E. Well, the -8E, that is the minimum size you need. -17 is nicer. It also comes in a quad 208 package. And if you have higher density FPGAs, you will be confronted with ball grid arrays, and that's not good for soldering at home.
So this one has 8,000 LUTs, is that correct?
I have no idea. No, it had. Yeah, that may be true. Yes. That seems to be what the number says.
Yeah, that would make shipment a lot easier for everybody. And
yeah.
You have local
I took a note. I will do that. And is there such a thing as a FIG mailing list, Kevin?
Yes, unfortunately, the guy who runs it is not accessible at this time. He had some issues that started with the COVID epidemic that he hasn't really recovered from in terms of his circumstances. So I can forward anything that you send me to mailing list, and that goes for any of you on this. On my email address is Kevin, or rather Forther at Comcast.net. Notice that it is not .com, but rather .net.
Oh, say this again. So this is Forther.
Forther at.
I have mailed you before, so I have your email address. Anyway. Yeah, so I will let you know once I have done the port, because then, but then of course I first have to acquire such a board in order to test what I have changed. Kevin, I don't hear you anymore. Yes.
Yeah, if you can't reach me through my email address, you can send me a message through Meetup. All of you should be registered on Meetup, and you should, for each meeting that you're going to come to, please set your attendance. Tell me you're coming on Meetup. And then for this is that when we have a meeting in the past, people can look at our meetings and say, oh, 20 or 30 people went to that one. There are actually hundreds of Meetup subscribers that have expressed an interest in our monthly meetings. So it's worth the rather small expense that I bear each. I think it's once or twice a year they ding my credit card for it, and it hardly shows up on the radar with compared to other atrocious expenses. I did want to mention that Sam put a link in the chat for the for Klaus's board, the details of that. So I refer you to that, and maybe Dave can put that in the meeting notes as well. I wanted to mention. Somebody else spoke up.
Yeah, Klaus said that he would like someone like in the United States to distribute the boards for him, and I'm wondering whether those boards have to be reflowed or put together basically.
No, these are old boards. I mean, the LFXP2 family is aged already, so I don't know whether boards will be available from Lattice anymore.
I will happily redistribute them for you over here if you wish.
Who is I? Brett?
This is Stephen Adele, Stephen A. You can't see my face. It's I don't have my video on this laptop, so I don't.
Please drop me an email, and my email address is on the first screen of the slides.
Okay.
Which I haven't sent them to you yet, Kevin. I will mail them to you.
Yes, more to the point, if you're presenting at the Zoom, your slides to Dave Jaffe for the website where they are published. I also wanted to mention that our YouTube channel has the video recordings each month. Brad breaks them up into individual presentations. So are we ready to move on from? I did
last word. Yes,
thank
you very much for breaking up for these YouTube videos and breaking them up. They are very helpful for me.
Yes, I wanted to mention that this month's presentation went a little longer. I know that Bill Ragsdale and others feel that YouTube presentations should be shorter, and it may be that for certain things like Klaus or Bob Armstrong, we want to be aware of that rule, but maybe ignore it in some cases. Kevin? And yes.
I was hoping to find out how many people are interested in getting one of these boards at, I guess it's 30 euros, right? You said?
Yes.
Klaus?
Yeah.
Is that with the chip on it?
That is a fully assembled board.
Okay.
I mean, these have been designed in Germany as a development board or experimentation board when the LFXP2 family came out. And then this was considered, I think it is now considered a legacy product. And I just bought the remaining boards that still were available.
Okay, why don't we do this? I will put a note on the meetup for the next meeting and say that there were boards available possibly. We will also send to the email list
Correct.
who's interested. Stephen, if you send me an email, I will we'll start maybe a little subtopic on a thread on this subject, making boards available in the US, and we'll see how many interest. Right now, is anyone that's online now interested in having one of these boards?
So it's one.
All right, I would make it count at one being Stephen self. All right.
Yes. I'll take. You said there were two boards. You said.
No, I didn't talk about two boards. It's one board. And
Okay.
and what I will do, I will look at what Lattice has available as experimentation boards, and if there is any that I can easily adapt.
Excellent.
Yeah,
Thank you.
it may be that the current generation of Lattice that is available might be better suited for this endeavor. In which case
that might even increase the performance of microCore.
Yeah.
How easy is it for somebody else to port the VHDL to another board? Is all the information available to do that?
Yes, and if I do that, I need half a day to get it running. I mean, okay. the thing that the abyss that has to be crossed is that the board reports back on the umbilical link.
Right. That means it would be as well easy to put it onto a Xilinx.
Yes. I mean, I don't know off the top. Or no, well, wait a second. I have ported it to Xilinx. I have ported it to Altera. I have ported it to Actel Microsemi and to Lattice.
Right.
And it is, and the VHDL code is VHDL 93, so it also works on legacy FPGAs.
No, the reason why I asked that is at the moment it is difficult to get boards with chips on it or chips. So the question is, the question was if one could go for availability rather for a certain type.
Yeah, that's easy enough.
Okay.
And what all you need is the development environment consisting of the synthesizer and the place and route suite.
Well, I know Steve, and he basically just implemented my own old processor and without any problems. So I would ask him if he wants to have a go at it as well.
What do you call my old processor?
Oh, about 40 years ago, I had a good idea. The chip was then done by a university in Silicon, actually, and I always carried it around. And then last year, I think I convinced Steve to re-implement it. It's an absolute minimum processor. It's basically nothing else than Amazon. It just takes packages from A to B, that's all. And so basically, even the ALU is basically 3 address locations, A, B, and result. So that's a very small processor. It exists, and I have it on one of these wonderful boards from Trent's. I don't know if you know the guys.
No.
Trent's Computer in Germany. They do nice little boards, you know, about Arduino size, Arduino Nano size. Basically just IOs and the USB on top. So both of the 1802 and as well this one, I think I have on one of these boards. Okay, you answered all my questions. Thank you very much.
That's great. I wanted to, Klaus, did you want to say something?
Nee. Thank you very much for your attention, and I think no questions remain.
Okay.
Oh,
yeah, I did
have one. Is there a user group? People who actually use it at the moment?
No. I have kept this sort of a secret during the past 20 years. During my professional life, I have just applied it to my own projects. And these presentations here are my coming out, so to speak. So the user group is hopefully ahead of us.
So I was talking about Klaus's time expanding from a short YouTube-friendly presentation to a longer one. Does anyone have any comments about that at this time? All right, then let's move on. I wanted to ask everyone to think about speakers, either if they want to talk themselves. There are a handful of people that have presented. If you don't want to present yourself, maybe think about who we could get that would be willing to present. Recently, is it Factor? Is that the name of the programming language?
Yeah.
Sam, do you remember? Factor. Okay. The Factor folks gave one talk, and they'd be willing to get in and do other talks if people could propose things that they wanted them to talk about. I inquired a couple of times about that, but I don't think anybody actually responded at that time. I'm not sure anybody was actually available or aware of those inquiries at the time. It wasn't clear to me, but if you have anything for the Factor guys to tell us about, if you know somebody that you'd like to have speak that might conceivably be willing to, please let me know. This depending on 3 or 5 people to give talks every month can't go on forever. Clearly, but I'd like this to go on forever.
And Kevin?
Yes, sir.
I have a couple of advertisements that might turn into talks later if you'd give me a few moments.
I would be pleased to give you a few moments.
Okay.
You're on.
I'm on. I'm climbing underneath my camera, so I can't really show at the moment. Show myself and what I'm going to show here, but let me.
Brad, you give him the spotlight.
Actually, what I want to do is share my screen. Share screen. And there we go. That one. So what, can you see my screen?
We can.
So this is what I'm working on at the moment, and we're giving away boards. This is the dev edge. And I can't tell what you guys can see at the moment. But this one is a very short, how can I paste that anywhere? I'm not sure I can paste that anywhere. Can you see the address though, up at the top there?
devedge.tmobile.com.
Yep, it's that simple. That's the freebie. We're giving away boards. And it is what I've been tearing my hair out on recently. And I'll talk when I can. But the boards are going away free. They are open source hardware as well as software. And then this Zephyr group, that is the OS that we are using, just had a conference, for the lack of a better term. And one of the attendees was Nordic Semiconductor, and they've got this very nice little dongle, which is super cool. It doesn't run Forth yet, but it runs Zephyr. So if you want to get into Zephyr, this is a very inexpensive $10 way to get in and play with it. And that, now stop share. Now we're back. And that's about what we've got at the moment. Not much, but just a few moments. Okay.
All right, thank you, Dennis. So what sort of time frame are we talking about for an actual talk?
You want to pin me down, and
I want to know if it's next month or 2 months, or if we should assume that we'll
I don't know.
We'll get to it when we get to it.
we are going into pilot mode beginning of next month. So we aren't actually shipping quite yet, but we do have a few select pilot people that we're going to start getting going on. So I don't know how bad or good this is going to be and how much time it's going to take me to support it. We've got a fairly large teams here supporting it. So it depends on when I get a life back again.
We wish you all the best with
Yep. Okay, I will go back to hiding again.
So, okay, folks, I have to go. Dinner is ready, and see you probably, I'm sure, next month. And by the way, I could give a presentation on a completely different topic, which is using the microForth check digits while compiling control instructions. You can do much more with them than just using them for check digits.
All right. That sounds great. Sam, are you ready to go?
No, but I'll go anyway.
All right. So that's Sam's version of the canonical response was born ready. All right, introduce yourself, Sam, and tell us the topic.
Okay, well, my name is Sam Falvo, and once my video comes up, this is kind of what I look like. And I will be sharing my screen here very shortly. Once I